My name is Timur, and welcome to our webinar. This is the first one in the series. We'll be focusing on how to get started with the exabyte.io platform. The agenda for today is we will go over 4 different chapters. I think the most important one is the first one. We'll go over the basics, and we'll speak about the entities that we are dealing with in the platform and how to share them, how to organize the service level, support requests, and such. And then we'll go over the entities in more details, specifically about, we'll speak about materials, workflows, jobs, and wrap up on that. So this is the introductory series. And here is what you need to know before we start. The goal of the seminar is to help users understand what exabyte.io is and how to benefit from using it. We have heard many requests, some complaints about the fact that it's somewhat difficult to learn the platform. There's a certain learning curve that is involved. And this is our attempt to solve it, to help people pick it up quicker. And this is a recurring series, which will be happening every first Friday of the month. And then every third Friday of the month, we'll be speaking about advanced topics. So this one that we are present in right now is about getting started. There is also a series about advanced topics. Now, every participant should be a registered exabyte.io user. If you are not a user yet, please go ahead and register. And every participant will receive this presentation in PDF format after the webinar. Highlighted text in this presentation will be a link. This webinar is recorded and will be made available online. And all the information contained here is also available at docs.exabyte.io. So you don't need to take notes. A little bit about myself. This is my personal Google Scholar page. I worked on density functional theory and materials modeling in general while at UC Berkeley. And it's during that time the idea about exabyte came to me. It felt that the way that we do materials modeling can really benefit from using some of the latest technologies like cloud computing and web services. And this is how I started to build the company. If at any point or after the seminar you have any questions, please feel free to contact me as timur@exabyte.io. Okay. All right. So here is the overview of the platform. Excuse me. It's quite a bit of a complicated picture. I do understand it. So if you want to look in more details and understand it a bit better, then you can look at this manuscript. The important concept here is that we have 3 parts: the part which is open source, and the part that constitutes the exabyte.io services platform in the cloud itself. And then there is an external elements part, which the platform does not include, but users still can use to ingest the data. Okay. And the important part that we're going to be speaking about today is the way that computational scientists are using the platform. And we are only going to focus on that during this presentation. All right, so we'll be speaking about how to use the cloud aspect and do computational science with the platform. So here is how the platform looks to the user. And as you are able to see in this screenshot, there are multiple different entities that are present as tabs here. So there are materials, there are workflows, there are jobs, people, and such. So we will be speaking about this exact entities in the first part of this seminar, the basics. All right. So we have multiple entities, but the most important ones are materials, material structures, the workflows or modeling workflows, which contain the logic about the simulations, the simulation jobs, and the materials properties. And in order to understand the relationship, we can look at this diagram, which represents the relationship to each other. So we have a material which characterizes a certain structure. We have a simulation workflow. And together, when they come together, they constitute a simulation job, which produces a property at the end, which can be attached to the original material. Now, the properties could be characteristic or descriptive, and that accounts for the properties that are produced during the simulation or the properties that exist before the simulation. And hence, they're colored differently on this picture as well. We have separated these entities on purpose to improve the modularity and cover multiple models and material types. It's often the case when we deal with simulations that material and workflow information, for example, is bundled together, but it makes it very difficult to go beyond the single model or beyond the single material type. And we have purposefully decoupled this information. This is still work in progress, and some boundaries between these entities could be blurry, but the data structures are well defined. And the data structures are defined inside this open source online repository on GitHub. And they're defined in the JSON JavaScript object notation format. And they're organized as schemas. Schemas that define the data component relations. I will explain it in a moment, but the important concept here is that this is all open source information, and we welcome contributions. So what we have today is the foundation, so the basic rules and how the additional material types, additional simulation types could be added to this repository, and an example for pseudo-potential density function theory. But as you may already know it, computational material science is quite a bit complex. And there are certain other techniques that we would like to add to it, and your contributions are encouraged. So if you look at the repository, and I know it's difficult to see here, but bear with me for a moment, we will see two important things. We'll see schemas. So this is an example schema of a material. It contains multiple properties like its formula, a unit cell formula, basis, lattice, and such. And then here is an example of a material which represents silicon. We see that there is a basis and it has certain coordinates, and there is lattice as well somewhere in here. So that's how we store the information. That's how we represent it inside the platform. Now, why it's important? It's important to understand because every single entity that you look at inside the platform is underneath represented by this JSON structure. And there is a way to extract this JSON structure so you can get the raw information about each of these entities. For example, if we go to materials list and click on expand, you are presented with exactly this data structure which contains all the information about the underlying material. Okay, so that's how the information flows under the hood of the platform. So just to summarize it, every entity user encounters in the platform is defined within the exabyte data convention, which is an open source GitHub repository. The definitions are meant as a unified format, able to incorporate multiple simulation types and multiple material types, and we welcome your contribution. The platform provides a user interface to work with these different data formats and impose actions on these entities, but there are multiple other access options. Besides the user interface of the web platform, we also have command line access and remote desktop access and the RESTful API. Okay. So now, when we speak about the entities, we also have to have the actors. So the users or multiple users that perform actions on the entities, and these are the accounts. Accounts can own and perform actions on entities, and accounts define different ways of how users can interact with the platform, which means that a single account, a single user could be a member of multiple accounts. And this two could be, two or more could be independent. So user could be doing actions as part of these different accounts independently. There are organizational or team accounts and personal accounts. Personal accounts have only one member, the person themselves. And organizational accounts have teams that have different permissions. So like read and edit. Account members have shared access to the account entities as it's set by the account administrator. You will experience it today as we are all the participants of this webinar are members of the webinar account. And you can use this account to do to poke at the platform and do calculations. So when we understand that there are accounts and entities, the next concept that we have to understand is how the entities are stored and owned. The entities are collected inside the platform in a way that each account has their independent entities separately. We call this entity collection. So when I first create a material, I want to have my own subset of materials that are completely independent of anybody else's. When I upload the data, when I import the data, when I do any kind of operations on it, I want to have my own subset. And by default, this is what users see when they log into the platform. However, since many people are likely working with similar materials, we collect unique entities inside a concept that we call entity bank. So a picture that we can illustrate it is given here. We have the account-owned entity collection that can contain multiple duplicate materials from different accounts. And then we have this mapping operation, which identifies the unique materials. And then inside the bank collection, we only have unique entries. Okay. And exabyte ID property of the entity inside this account collection refers to the ID of the entity inside the bank. So unique ID inside the bank. Now, there could be private or public data access options. And some accounts have the private data, others do not. And if the account has private data, then the entities that are created inside the bank are not accessible to any other account, unless they have created exactly the same entity independently. And if the account doesn't have private data, then everybody else can see the entities that they create. For example, if I created silicon and I do not have this private data option, then everybody else on the platform, when they go to materials bank page, will be able to see silicon as a material. Okay. We have a way to import entities using this helper action from the bank. And the workflows and materials could be imported to user-owned collection using this action. And we have a set of curators, or the account that is established by the platform administrators. And we curate a set of workflows, for instance, to do basic calculations like total energy, band gap, and such for density functional theory. So if you look at materials or bank workflows and see curators there, when you search for a particular workflow, you can know that these are tested, and these are the workflows coming from exabyte-io. Now, very briefly about the service level. The service levels define the features available to accounts. And there are things like subscription fee and compute allocation, number of people within the account, the disk space, and such. And we have multiple different service levels, including free. You can research it in your own time. But the important concepts here are that the service levels, together with the compute categories, define the final price that users pay for executing calculations. So besides the accessing the platform fee and the data storage fee, the most important fee comes from running calculations. And if we are not speaking about the free account, then the final price comes from a combination of compute categories, which could be debug, nature, ordinary, or saving. Debug, for example, is are resources that are always on, so there is little to no wait time, but they come at a premium cost. And then the modes could be different in a way that with regular mode, we are scaling in succession. So one compute node is added into our computational infrastructure every time the new job comes in. And then with the fast scaling, if, for example, a user submit 10 different calculations, we provision 10 jobs and provision 10 nodes in parallel, 10 compute nodes. So when we combine this category and mode, we get the queue. So for example, when I take ordinary from category and regular from the mode, we get an OR, ordinary regular queue. And that's how you can quickly identify what type of queue, what type of service, what type of operations do you expect from this queue. Then the numbers here also stand for the maximum size of the node, the maximum size in computing cores. So OR4 has 4 cores. I think we're running a bit over time, but I think it's good because the basics are important. Let's cover those and we'll speed up during the other 3 parts. So here is the main interface of the platform. Again, there is a header and 2 sidebars, a footer, and a support widget here. So you'll be able to toggle the headers. You can click on the very corners, the left corner and the top corners of the screen and the right corner. And they will trigger the corresponding sidebars. To be able to submit support tickets, you can use the support widget in here. And this is how it looks when you submit a support ticket. We strongly encourage people to provide additional information like screencasts and screenshots, because otherwise it's very difficult for us to understand the nature of the problem. We can attach those to the support widget. And sometimes there could be an interactive chat here when we have a person waiting online to receive the tickets, the communication. So you can just speak with us in real time. Now, we have also enabled a different type of chat for people who are not yet logged in. And if you're already a logged in user, please do not use this option. This is only for people who are still exploring whether and trying to figure out whether or not they want to become an exabyte registered user. Okay. All right, so I think I am through with the first part of this presentation with the basics. Let's see if we have any questions. Do we have any questions? Okay, it doesn't seem like that. Just give me one moment. I will try and pull up the chat to make sure. Okay. We still have some time to go over the questions, but if there's no questions, I will just proceed with the rest of this presentation. So before we go to the rest of this presentation, I want to make sure that everybody is indeed logged in and everybody has the access to the webinar account. Okay. So if you are logged in, and then you can use the right-hand sidebar and click on My Accounts to navigate and use the webinar account. So open the right-hand sidebar by clicking on your name, step number 1 here. Then click on My Accounts to open the list of accounts and click on the webinar to start using the platform as its member. And as we go forward and go through the actions that we can perform on the entities, you can follow along. I will be showing the videos and demonstrate how to do the operations, but you can follow along this explanation by repeating these actions inside the platform. And you should be able to do that, and you should have all the necessary prerequisites satisfied within the webinar account. So we'll be speaking about materials in this chapter. And the first action that I'd like to speak about is how do we upload materials. Most of the time people already have a set of materials that they work with. They come in, say, PostCar or CIF format for the crystalline materials. And here is how you can import a file that contains materials structural information into your platform. We start with clicking on the upload action inside the materials Explorer interface, so where we see all the materials. And then when we click on the upload, which is this action that I'm demonstrating here, when we click on upload, we are presented with the upload interface. It's a model where we can select multiple files. So we click on select items, and we can select multiple files from the disk, from our local storage. Here I'm selecting multiple PostCar files, 3 of them. And when I click open, these files show up inside the interface. So they are not yet imported. They are just selected for importing, for uploading. So these files are presently selected, and I can click on them and make sure that the content makes sense. And we can see visualize the content of each file. And then I can select it and tag. So we can add tags to a particular file. So I selected the file number 1 and added tag 1 and tag 2, separated by comma. And in turn, we can see that there are 2 tags added to this file. So this is a way to tag the file before we upload it. And then I select all the files inside the list, and I click on upload. So that is how we actually upload the information and create the material entities inside the platform. Here are the check marks that indicate that the information indeed was uploaded. And there is a green notification that shows me that material successfully uploaded. So at the end of it, I close the pop-up model, and I see that 3 materials are created inside my account. And one of them indeed has 2 tags that I created for these materials. All right. So this is how we can upload the information and tag it to be able to search for in the future. So if I search for tag 1, I will be able to find this material quickly. Okay. So the next action that I'd like to go over is how to import. In this case, we import from an online database. So instead of uploading a local file, we are importing directly from an online database. In this case, we are dealing with materials project. So the import action looks like a cloud icon in the actions bar. We click on that, and we are presented with a dialog again, where we can search for the materials that we would like to import. And here I can proceed by typing the formula for the material that I'd like to import, magnesium dioxide in particular. So here I can see a quick summary of the materials that are presented. If I click on each one, I can see detailed information about this material as well. It's not demonstrated in the video, but that is the case. So magnesium dioxide, I select the first entry in the list and click on import to actually initiate the import action. We see the loader while the action is running. And when the action is finished, we see that the material has indeed been imported into our entity collection. Okay, when we close the dialog, we see the material at the top of the list. It is named according to its materials project ID, and it retains all the tags and all the structural information, of course, coming from materials project. So it's lattice, basis, and tags, and this is the visualization. All right, this is how we import a material from materials project. Now, a third way to deal with ingesting or adding materials information into the platform is by importing or copying it from the entity bank. As I demonstrated during the first section, we have the collection of unique items. For materials, we call it materials bank. And since many users are creating materials, it's likely that anybody new who comes to the platform can find these materials inside materials bank. So here I'm going to demonstrate how to import materials from bank. And there are 2 ways to access the bank. In this video, I'm demonstrating the more difficult ones. So we open the left-hand sidebar, click on the bank entry, and then select materials to open materials bank. Inside the materials bank page, we again search for magnesium dioxide, just like in the previous video. And we see that there is an entry that somebody else have created. And we see its lattice parameters. We can also see additional options here if we add additional columns by clicking on these 3 dots, which is not what I'm demonstrating in this video, but that's also a possibility. And then if we click on the copy action at the top, we will be able to copy this item into the private collection owned by our account. So the notification here says that the items are copied to a private collection successfully. And then when I come back to my collection of materials, I see magnesium dioxide at the top. Okay, so there's 3 ways that we can ingest materials information: by uploading or importing it from either online database or from materials bank. Now, today we have an import from bank action, which will take you directly to the bank. So in case of workflows, it will be the workflows bank. In case of materials, it will be materials bank. And we also have a way to search for materials in an advanced way. Sometimes searching by formula is not enough. So clicking on the advanced search dialog will allow to use a more sophisticated way to filter for the materials that are shown. Here is a logical query constructor that is based on and or logical conditions. You can see here that and is highlighted twice. So we will use multiple logical conditions here. We start with the formula that contains aluminum. And then we will add an and condition here. Select one of the properties that are available, like lattice type, model, method, for the properties that were extracted in this particular case. And I'm selecting the unit cell volume. And I'm putting a certain number and making sure that the unit cell volume is less than that number. So adding another condition here, which is tags. So really this search query contains three options that are connected by AND logical condition. Formula contains aluminum, volume is less than 80. This is an angstrom cube. And then tags that contain high pressure. When I'm running this query, I get the result, which is the material of choice. Okay, so this is how we apply advanced search on the materials collection. It could be done either on your collection of materials or inside materials bank as well. Now, the next option that I'd like to go through is how we create materials or how we design them. So once we have ingested, usually people start with something that they already have created before, like a file from a local disk or a material from a third-party database. And then they usually need to modify these materials to create some things like surfaces or supercells or such. So to do that, we can use the create button, create action, and open materials designer. And this is how materials designer page looks. There is a header menu. There is a list of items that are presently active inside materials designer. Like silicon FCC is one of the items here. There's a crystallographic data panel, which contains the crystal lattice and crystal bases. And there is a 3D interactive crystal viewer, the fourth part. Something that I'd like to note here is that Materials Designer is a standalone open source JavaScript application. So you are welcome to contribute to developing additional features. All of this is open source and you can run it on your own inside any web browser. So the materials that we work with inside Materials Designer can be imported from materials collection. So in this case, we are only restricted to using the materials that we already own, because only those materials are editable to our account. Right? So here I'm selecting the input-output menu item, and I can import a material from my collection, as it says here at the top. These are multiple materials that I have in my collection in this video. And I can search for one of them. Here I'm searching for a tag and select it to be imported into this Materials Designer interface. I apologize for this ambulance going through. I'm just going to mute my microphone for a second. Okay, I think it's gone, so we can continue. So what happened here is that I have had a single material active inside the interface before, Silicon FCC. And then I go through the process of importing another material. It's a familiar interface. I'm selecting the material, clicking select items in the actions bar. And now I have two. And I can switch between the two by clicking on the corresponding material inside this items bar. Okay. So this is how we import a material into the materials designer interface. Now, there is another option of how we can deal with materials information. There are many more other options that are present inside materials designer. As you can see, there are multiple other header menu options, but going through them is something that we will do during the advanced webinar. So if you are interested in learning more about materials designer, how to create material arrangements like supercells or surfaces, we'll go through that during the next seminar, which will be in 2 weeks. The basics of how we can deal with materials information, another possibility comes through the RESTful API. This is an advanced topic, but I just wanted to demonstrate that it's a possibility again. We have a set of examples arranged as Jupyter notebooks for people who are familiar with Python. And there is a repository, open source repository online available on GitHub. I will share this presentation, and if you click on this link, you'll be able to see that repository. So if you look at this repository, follow the README to set up the Jupyter notebook environment, you will be able to communicate with the RESTful API and then create materials directly by uploading the data structures that we have very cute in the very beginning. So if you create a material structure according to exabyte data convention, you can use the RESTful API to upload it directly into your collection. Okay. All right. I think we probably a bit over time for this section as well, but let's see if we have any questions. Do we have any questions? Is it clear how to ask questions in general? Can somebody try and type something in the questions panel so that we check the connection? Okay, all right. Good, so no questions then. So we're proceeding to how to deal with workflows, the second type of entities. And usually with workflows, we are not starting with something that we are uploading from the disk because of how the workflows are structured inside the exabyte platform. It's still a new concept, and I don't think we have many other people using this type of concept today. So we usually can start from importing workflows from Entity Bank. And here is how we do that. So we have a set of template workflows available inside the Entity Bank for workflows, the Workflows Bank. We can open its page and then search for the workflow of interest. For example, here I'm searching for the band structure workflow. And as you can see, there are multiple examples already present. And then I can select one of them and click copy. When I do that, the workflow is copied into my private collection of workflows for my account. And you can see there is a notification shown that the item is copied to your private collection successfully. And when I go to the list of workflows for my account, I can see this exact workflow. So here is when the workflow becomes available to me for edit. So I can edit this band structure workflow that I just imported from the bank. Now, to be able to understand how this data is structured and how to work with it, we need to have a quick introduction about the inner structure of the workflows. The workflows can be represented by this flowchart. So the green part here is a workflow which consists of two sub-workflows. And this is just an example. There could be as many sub-workflows as we want. And sub-workflows in turn consist of units or elementary calculations. And these units can be assembled in sophisticated ways. So we think that altogether, this concept forms the logic included in the workflow or the flowchart, the algorithm. Each subworkflow must be specific to a single simulation engine on purpose for modularity and reusability. For example, subworkflow 1 can correspond to VASP, subworkflow 2 can correspond to Quantum Espresso, and so on. Subworkflows contain model and method. For example, model could be density functional theory, method could be pseudopotential. And if you look in more details at units, we see that units actually constitute these elementary calculations. So if I'm running something like pw.x out of the Quantum Espresso suite, then a single application of this unit for this executable will constitute unit 1. Units can have different types. For example, there could be execution units to run Quantum Espresso, run pw.x. There could be assignment units where we set a variable, a equal to b. And there could be condition units. So the workflow and the associated data are connected to each other. The output of unit 1 at the runtime can be accessed by unit 2. And as the calculation progresses, this capability is retained. So unit 4 can access the output of unit 1, and so on. Execution units have executables. For example, pw.x is an example executable. And executables can also have different flavors. For example, in pw.x, we can have self-consistent calculations. And we can reuse this flavor in multiple different sub-workflows for modularity and reusability again. So here is how the workflow designer looks. So once we understand how the workflows are comprised out of different small units and sub-workflows, we can understand this interface a bit better. So we imported a workflow, we can navigate and see it and modify it. And header menu here contains the name of the workflow and some actions, basic actions imposed on the workflow itself. The list of sub-workflows here is on the left, the items list. And then a panel which demonstrates the details of the work of the sub-workflow is given as number 3 here, Subworkflow editor. So here is an example of how we can work to add or delete a sub-workflow to a workflow. We click on the action on the plus button inside the Subworkflow panel, and we are presented with a dialog of where to add a sub-workflow, either to append to the current active one or to prepend. If I select to append and I click apply, then a new empty sub-workflow is added. It's empty because it doesn't contain any units, but if you navigate into it, we can add units to it, or in this case, I'm deleting it as well. Okay, so this is just an example action that we can impose on workflows. In this case, I'm adding a sub-workflow, a second sub-workflow to this workflow. Now, the actions that are available to modify sub-workflows are given in its own panel. Again, there is an actions menu bar with multiple buttons here. There are certain tabs that show the properties of the sub-workflow, and there is a units flowchart. Without going into too much details, here is how we can see the content of the units that correspond to the sub-workflow. We can do that by clicking on the units flowchart and a particular unit inside the flowchart. So if the currently active unit is highlighted in gray, the unit type is also shown here by its first letter. So E, for example, here is equal to the execution unit. When we click on the unit, this orange circle denotes the click, we can open its detailed view. This is how it looks. So this is the PWSEF, the unit which has pw.x as an executable, and its flavor is the self-consistent field type calculation. There are certain properties that are pre-selected for this type of calculation. Like we extract atomic forces, Fermi energy, total energy, pressure, and such. There are certain monitors that are associated with this unit. We can see the standard output, and we can see the convergence of electronic structural calculation. And then in the next section, we can see which unit will be following this current one, as well as the input templates. So here is the input file for Quantum Espresso at the very bottom. And to understand the concept of the template, we have to look at this slide. So we have two tabs here for PWSCF input. One of them is a template, the other one is a preview. If you look at the template, we see that there are multiple variables that are included inside this curly braces. And there's also dotted notation that is used inside these variables. And the reason why we use these variables is because there is template data that we make available for this template that will produce the final text. So here, the template data comes from a material, and which I will be speaking about when we will go over the jobs. But in the beginning, we spoke about the jobs being a combination of a material and a workflow. So here is where the information from the material comes in play. And there are things like the lattice type, for example, above in Quantum Espresso notation, the number of atoms, the number of atom types, and such. So once we combine the template and this information, the template data, as we call it, we get the rendered or textual output of the template. And it can be accessed inside the preview tab. And this is what we call the first render, or the render on the web. There is also another type of render that happens on the computational cluster. As you can see here, there are job work directory. We don't know when we deal with this input file beforehand what the job directory is going to look like. And it really is not something that users need to worry about, where exactly our system will put this calculation. So we leave it as a variable that will be rendered during the runtime. So there is a set of variables that are rendered during the second render or runtime render, and job work directory is one of them. So what happens is that this textual file is sent to compute cluster. The calculation is started, and during the second render, the job directory is substituted. The other, just like with the materials, there is another way to deal with workflows, and it again is through the RESTful API. This is an advanced concept, but I just wanted to demonstrate the possibility. We are able to see the actual data structures, the JSON content of the workflows, by using this exabyte-io examples repository. And you can follow those 3 steps from the presentation that I will send to the participants after we're done. All right, do we have any questions about the workflows? Still no questions? We have some time, so we can go to the questions at the very end. All right, let's go to the job section. At the very beginning, I was speaking about jobs as a combination of materials and workflows and the computational parameters. So here is how we can create a job. But before we start, we need to make sure that certain conditions are satisfied. First of all, we need to make sure that we have created the materials and created the workflows. We have separated these concepts on purpose to simplify the interface and to make the data usable and assert consistency. So materials and workflows must be created before we create a job. We also need to assert that the account has enough balance to perform these calculations. And we need to make sure that the account has enough disk space or disk quota for this calculation, the data that will be produced during the calculation to fit into it. And the first step that we need to undertake to start creating a job is to navigate into the desired project. The concept of the project is really simple. It's just a collection of jobs. And usually this is a project that computational scientists are working on, for example, studying a particular problem, which will have a collection of simulations related to this problem. So if I'm working on something like high throughput study of band gaps for thin film materials for 2D materials, there could be one project. And then if there's a completely different one, like a study of a chemical reaction, I would name it as a project number 2 or something like that. But there's also a quick way to create a job by using a create job action inside the left sidebar, as I'm highlighting here. In this case, we are just going to navigate to the default project directly. Everybody has a default project, and this is a quick way to create a job inside it. So once we do that, once we click on create job, we are taken to this job designer interface. As you can see, we have this basic concept of designer that is applied to all the entities, materials, jobs, and workflows. And here's how the job designer looks like. There's a header menu that contains the name of the job and action buttons. And there are 3 tabs: materials tab, workflows tab, and compute tab. First, we need to select the materials for the job. And here in this video, I'm demonstrating how we can do that. We need to go to the header and click on these 3 dots to open the dropdown. And inside this dropdown, we select the select materials action. We click on select materials, and we are presented with the pop-up, the model that contains the list of materials that are owned by our account. So this is the materials that are owned by our account that we have already imported or designed or uploaded, right? So all materials that are available to my account. And then it's just a simple process of selecting materials. Here I can select multiple, as the video demonstrates. And I click on select items action to actually add it to the job. Okay. As you can see here, while the action is running, there was a quick moment when there is a loader here, which means that the job designer is in the intermediate state. The materials are being added. It's still loading them. And once everything is done, the check mark is back. Okay, so here I added multiple materials, 6 to be precise, and then I can select each one of them and visualize, make sure that I'm dealing with the right material structures. This is a quick way to preview them. Okay, so this is how we can add materials to a job. I started with 1, and I added 5 more materials. Actually, no, I selected 6 more to substitute for the one that I had in the very beginning. This is what happened. The second step is to select a workflow. And now, just like with materials, I click on 3 dots here to open the dropdown and click on select workflow. And I'm presented with the list of workflows that are available to my account that I have imported or designed again previously. And I can select one of them, click on select items. And when I navigate to the workflow tab, I can see this exact workflow that I previously. In this case, I'm selecting the phone and density of states and dispersions workflow. Okay. And then the third step is to set up the computational parameters, like the time limit to select the computational cluster, set up the queue, the number of nodes, and some advanced options if necessary, as well as the email notifications. The process of selecting compute parameters could be quite complex depending on the materials. Some materials with larger supercell, with larger cell, can require multiple computational nodes, and we can use things like GPU computing here. But this is really an advanced topic, So we'll go over it during the next webinar. I'm not going to focus on it right now. In the very beginning, we can just keep the computational setup as default, just to run a simple calculation. You can also notice here that we have formula in the name of the job. This is a variable that will be substituted by one of the materials. Again, we have multiple materials that we have selected in the first step, and the formula of each material will go into the name to understand when we create the job, which material it corresponds to. Now, the next step is to click the Save button to actually save the job. And if we have multiple materials, it will create multiple jobs for each, one for each one. So we click on the Save button, and we will be taken to the list of the jobs that are created. There are a few notes about the job creation. First of all, workflows cannot be modified during the job creation. And we did that on purpose to simplify the user interface component for the job and to assert the data consistency. What I mean by that is that if users would be able to modify the workflows directly during the job creation, it could lead to inconsistencies. If they could change the model types, for example, instead of density functional theory, use molecular dynamics or something like that, it could quickly become very difficult and very messy. So we on purpose have removed this capability. The users should modify and edit the workflows first inside the workflows designer, and then select this modified workflows during the job creation. It is still possible to edit the unit input preview directly inside the job, but we would advise against that. It's only should be used on for any kind of critical scenarios where it must be done. Multiple materials can be selected for either high throughput type job creation when we create multiple jobs, or for multi-material jobs like NEB calculations, chemical reactions. Where we have multiple images, we can select multiple materials during the job creation. Materials data then is fed to the workflow unit input files for multiple materials at a time. Jobs can also span other jobs, so they can start other jobs while they're running, and they can wait for their execution. And this is again an advanced topic that we will cover in a separate webinar. All right, so once we created the jobs, here is how it's going to look like. This is the list of the jobs. And the ones that we have just created, they have this P status, which stands for pre-submission. And here is how we can run a job. We can select, click on three dots and open the drop-down of actions available for this job and click on run. So this is a very simple procedure. Once we do that, the job goes into submitted status. Yes, we see the notification. And quickly, since this is a debug queue job, there's little wait. This is all real time. It quickly goes into the active status. And inside the active status, I can see how long the wait time was and how long the job was running for. While it's still running, the job runtime has this plus as it's ever increasing. When the jobs are finished, you can see this F, green status. We can see the job runtime right there. So the silicon band structure job, for example, was waiting in the queue for about 4 minutes and was executed for about 2 minutes. Okay, we can track the progress of the job by navigating into it. So here I'm clicking on the silicon band structure job, going inside it, and while it's running, it's shown in orange. So orange denotes the active job, and we can see that the band structure workflow is currently active. And if we scroll down, we can see that the PWSCF unit is currently active as well. If we click on it, we will be able to see the output updating in real time as the calculation is progressing. And then there are certain charts like this convergence chart, which is also updated in real time. So we can see how the self-consistent calculation is converging. And when the calculation for this unit is done, it is shown in green. And the next unit, as we see, is active. All right, so this is how we can track the progress of the job. And when the calculation is finished, the whole job is shown as finished in green. And we can access the results in files that are produced during the job. For that, we again can click on the job name, and you can notice two additional tabs that appear inside this job viewer. Results and Files tab. In the Results tab, for each sub-workflow and for each unit, we have the results of this corresponding unit. So Subworkflow band structure and its unit PWSCF have produced these following results: total energy, the pressure, Fermi energy, total force, and such. Okay, which are listed here. And then the PW bands didn't really produce any results because we didn't ask for it in the very beginning. And then and then the bands.x, the post-processing unit, produced the final band structure. And here's how it looks like. If we navigate back to the top, we can click on the Files tab. And here are all the files available and created during the job. We can download these files, we can visualize them right there inside the web interface. Okay, so here's how we access the files. Now, there is also a way to use command line to execute the jobs. Many people start with that, experienced people especially. And instead of going through this in details today, I just summarized in giving you a couple of links that you can follow on your own time. So there is a directory that we make available to every user that contains JavaScript templates. And if you copy that directory and use the JavaScript templates inside this directory, you can quickly get up to speed with the command line usage. And you can click on the links that are available in this presentation to learn more about the command line actions and how to execute them. Okay, I think this is mostly it. And I think we have about maybe a few minutes to go over the questions. Do we have any questions? I'm seeing the few attendees. I think right now it's the time to ask. No questions at all? Would you like me to go over anything, any other topics or anything in particular that you have in mind, since we have maybe a few minutes? Okay, looks like the communication might be broken on my end, or you really don't have any questions. Either way, so we are done with this presentation, and I think it's been a lot of information in a very short time period. So what everybody will receive as a follow-up to this webinar is a copy of this presentation, and you can follow it along on your own time. And again, this presentation contains the links to the documentation pages, so you can click on each of these links, highlight the text, and do this exercises on your own. If there are no other questions, then I'm going to call this seminar finished. And when we are finished here, we'll also produce a recording, so you can come back to this conversation and follow it along again on your own time. All right. So thanks, everybody. And we'll see you again, or maybe see your colleagues again next month or in 2 weeks for the advanced topics.